In the last class, we have seen DC generator can be operated with a separately excited field. When this field excitation is supplied from a separate source. However, it is not necessary to excite the field winding from a separate source. Instead, the voltage generated by the generator itself can be used to provide the field current, in which case the connection will look somewhat like this. Normally, a resistance is included to control the field current. This is the terminal voltage Vt, this is load current IL, this is armature current IA, this is field current IF. In order to understand how this circuit works, let us first assume that the field is unexcited, that is, this switch is open. With the field open, if the generator is run at rated voltage at rated speed, initially the field current is 0 and the generated voltage will be equal to the residual voltage, and if field is current flows, then the generated voltage will follow the OCC of the separately excited machine. This is the plot of E. Now, initially the field current is 0. At this point the machine is run at its rated speed and this switch is closed. As soon as the switch is closed, there is a current IF that will flow in the field circuit. Its magnitude will be equal to the generated terminal voltage, which is same as E here, divided by the field resistance. So, this is the field resistance characteristics, this is field load line, however, we see that if this field current flows in such a direction that it aids the residual magnetism, then the induced voltage in the armature will increase, which will then send more field current, which will again increase the induced current voltage, and this process will continue till the voltage across the intersection point of the field load line with the OCC. This process is called the self excitation of a DC shunt generator. Since the field winding is connected across the armature terminal, this is called a shunt connection, or the generator is called a shunt generator. For this shunt generator, then we can write V t equal to E minus E b, which is the brush contract drop, minus I a R a. Also, V t equal to I f R f equal to I L R L and I a equal to I f plus I L. These are the steady state equations of a DC shunt generator. Now, it has to be understood that this self excitation process requires certain conditions to be satisfied before an appreciable voltage is generated across the terminal of the generator at no load. Let us look at those conditions. If this is the OCC of the generator at rated speed and this is the field characteristics V t equal to I f R f at no load, V t equal to E minus I f R a. If we neglect the drop due to the small field resistance, then V t is approximately equal to E, that is the operating point at no load is determined by the intersection of the OCC with the field load line. So, this is the voltage at which the DC machine will excite to. Clearly, the voltage at which the DC machine will excite will depend not only on the OCC, but also on the field load line. For example, if the field winding resistance is increased, this is R f 1, this is with R f 2, then the voltage at which the terminal voltage of the machine at no load will change from E 1 to E 2, and if R f 2 is larger than R f 1, E 2 will be smaller than E 1. We can conceive a situation where the field resistance is such that the field load line is tangent to the linear portion of the OCC, in which case the excitation voltage will be E c. Clearly, if the field resistance is anything more than F c, then the induced voltage will drastically drop. There will be almost no induced voltage at no load, and in which case it will be called that the machine fails to excite. Therefore, we can see that self excitation does not occur at for all values of field circuit resistance, there are in fact 3 conditions for successful self excitation. First of all, there must be residual flux in the machine. Second, residual field coil connection should be such that field current assists residual flux. So that as the field circuit is connected, the flux keeps on increasing. Third, the field circuit resistance must be less than the critical resistance of the field winding at the operating speed of the machine. It is to be noted that the critical field resistance is not constant. In fact, it is depends on the machine operating speed, which can be understood from the next diagram. Let us consider the shunt generator operating at a speed of n1 when the OCC is given by this curve with a given field resistance. The operating no load voltage is determined by the intersection of the field load line with the OCC. Now, we know that the OCC is proportional to the speed of the machine. So, at another speed n2, it is entirely possible that with the same field resistance n2, now the OCC is tangent to the field load line. Evidently, if the speed of the machine is further reduced, then with the same field resistance RF1, the machine will fail to excite. So, for every speed of operation of the DC shunt generator, there is a critical field resistance below which the machine will fail to excite, and also for every field resistance there is a critical operating speed below which the machine will fail to excite. Therefore, the third condition should be read as the total field circuit resistance must be less than the critical field circuit resistance at the given operating speed of the generator. If these 3 conditions are satisfied, then a DC shunt generator will go into self excitation and produce rated voltage at the terminal, provided the field resistance is excited accordingly. It should be understood also that the terminal voltage at the generator at no load can be adjusted by controlling the field resistance. For example, at a given field resistance Rf1, the field current is If1 and the generated no load voltage is E1. If the field circuit resistance is increased to a value of Rf2, the no load voltage as well as the field current required reduces to If2. If Rf1 is larger than Rf2, then Rf2 is larger than Rf1, then E1 is larger than E2 and If1 is larger than If2. Therefore, the no load terminal voltage of a shunt generator at any operating speed can be adjusted by adjusting the field circuit resistance. However, as we have seen for separately excited DC generator, it is more important to find out the output characteristics, that is the external characteristics of a shunt generator. For a shunt generator, we know E equal to V t plus I a R a. If we neglect the brush contract drop, E equal to k phi omega r, phi equal to some nonlinear function of I f. Also V t equal to R f I f and I a equal to I L plus I f. If we plot the external characteristics of a DC shunt generator, it is remarkably different from that of a separately excited DC generator. Even if the two machines are adjusted such that they produce the rated voltage at no load, both a separately excited machine and a shunt machine, if they are adjusted to produce the same no load voltage, for a separately excited machine the terminal voltage will drop, but for a shunt machine this voltage will drop much faster. In fact, if we increase the load the load current will increase up to a certain value, after which it will decrease, and even when the machine is short circuited, there will be only a finite load current ILSC flowing into the machine. So, this is the external characteristics of the same machine run as a separately excited generator. And this is the characteristics when it is excited as a shunt generator. In fact, these external characteristics can be obtained from the OCC of the machine graphically. The procedure is as follows. Let us first draw the OCC of the generator. This is the generator OCC. This is the field load line. So, at no load, the terminal voltage is approximately given by this value. So, if we plot the external characteristics, versus I A, if we draw E t V t, then this point corresponds to the armature current of I f almost 0, very small. At any other armature voltage, at any other armature current, it should be appreciated that the difference between the OCC and the field load line given by E minus I f R f, that is equal to E minus V t. This is nothing but I A R A. So, this vertical distance between the OCC and the field load line is nothing but the armature drop. Therefore, we can find out the terminal voltage by the following procedure. For any armature current, let us take the corresponding armature drop OC and draw a line parallel to the field load line. So, that the vertical difference between these two lines is always equal to OC, equal to the IARA. We see that this load line intersects the OCC at 2 points, at A and at B. The vertical distance between the line section A O dashed and B P dashed are same as IARA. Therefore, for the same armature current IA, the terminal voltages will have two values, one corresponding to the point O dashed the other corresponding to the point P dash. In a similar manner, other points can be drawn two points are of importance at terminal voltage equal to 0, the vertical IF equal to 0. So, the terminal voltage is 0, the induced voltage is given by the residual voltage, hence the short circuit current will be the residual voltage E residual divided by R A. This will be ISC. The maximum current that can flow in the armature of this DC machine can be obtained by drawing a line parallel to the field load line and touching the OCC at one point. So, the vertical distance of the point where this characteristics touches to the field load line is the maximum IA, this is P, this is Q. So, IA max equal to PQ by RA. And the corresponding terminal voltage is this point. So, this is and the external characteristics can be computed like this. This is the procedure for drawing the external characteristics of a DC shunt generator neglecting armature reaction. Please note that in this analysis we have neglected the armature reaction, we have not considered any drop due to armature reaction. Now, if we want to incorporate armature reaction, let us see how this procedure will modify. Again we start by drawing the OCC of the generator. As well as the field load line corresponding to the field resistance. To find out the no load terminal voltage. since at no load there is no armature current, there is no armature reaction. So, the terminal voltage is given by the intersection. At any other load current, at any other armature current IF, we know that the armature reaction corresponds to the armature reaction then corresponds to a negative equivalent field amperes. Let us say at any given armature current IA, the corresponding equivalent armature reaction flux is OB, and the armature resistance drop is given by BC. Now, let us draw a line parallel to the field load line through the point C. Again it intersects the OCC at 2 points M and N. Now, let us draw a line parallel to OC from M and N. Then we can draw the triangle OCB at points M and N. M, M1, M2, N, N1, N2. Obviously, M1, M2 equal to OB, which is equal to effective Demag armature reaction in equivalent field amperes and M2 equal to IA RA. Therefore, for a actual field current corresponding to O01 and a actual armature current corresponding to IA, the effective field current will be IF actual equal to O01 and AR ampere armature reaction demagnetizing field amperes is M1 M2. Therefore, the net field ampere is IF net equal to O02. The corresponding induced voltage E equal to MO2 and IA RA equal to M1 M2. Therefore, corresponding to a field current of IA, there will be two terminal voltage given by O1 M1 and Q1 N1. So, these points can be now drawn on the external characteristics. For the short circuit condition, the terminal voltage, the field flux is very small, therefore, there is almost no armature reaction effect. Therefore, the short circuit current will still be residual voltage by field resistance ISC. For the maximum, again through the maximum current we draw a line parallel to field current. Then we extend the triangle here. For the maximum armature current, then the effective armature reactance, armature reaction demagnetizing amperes in equivalent field ampere will be O B dashed and the armature drop will be B dash C dashed. Therefore, we draw a line parallel to O C dash from this point, and the point where it intersects with the field load line gives the value of the maximum value of the terminal voltage at maximum armature current. And if we draw a triangle from here, then IA RA equal to this length, hence the IA can be found from there. This will be IA max and the can thus be constructed in this fashion. Hence, we see that in a shunt generator, the terminal voltage drops much faster than that of a separately excited generator. The reasons being, at in a separately excited generator, the armature current drop causes reduction in terminal voltage as well as armature reaction causes reduction in terminal voltage. However, the field current remains constant. In a shunt machine, since the field winding is connected at the terminal of the generator, as the terminal voltage reduces due to loading, the field current also reduces. Hence, the terminal voltage in a shunt generator drops much faster than that of a separately excited generator. It is to be noted though, in fact, even under short circuit condition only a finite amount of current flows in the armature. The armature current never exceeds this maximum limit. However, the normal operating region of a machine is much below this I max. Hence, even though at short circuit the current may be smaller than the rated current of the machine, transiently if the terminals are shorted, the armature current can exceed the rated current of the machine and can damage the commutator segments. Now, again let us look at the previous problem, the same machine, in case it is operated as a shunt generator, how the terminal voltage will vary. In this case, this was the given machine data, that is 3.3 kilowatt, 110 volt, 1500 rpm, 4 pole machine. The open circuit characteristics is given by this table. The armature resistance is 0.2 ohm, the number of field turns is 200 amperes, 200 turns, the brush contract drop is 2 volts. Then we are also mentioned that the effective armature reaction ampere turns, AR ampere turns, equal to 1.5 times armature current IA. If this is machine is operated as a shunt generator, let us try to find out the terminal voltage, first by neglecting armature reaction and next time including armature reaction. The first step in solving this problem would be to draw the OCC of the generator. From the given data, at no load the induced voltage is 5 volts. Let us say this is 0. Let us say this is 0.5 amperes. This is 1 ampere, this is 1.5 ampere, this is 2 amperes and this is 2.5 amperes. This is this is 40 volts, this is 80 volts, this is 120 volts. This is the OCC. It is further said that the field resistance is adjusted so that at no load with rated field current of at no load the machine generate rated voltage. So, this is the field load line. At the machine will generate 110 volt at no load and the corresponding field current will be 1.5 amperes. So, if we neglect the armature reaction, then in this diagram the length of this OB is 0. So, at any armature current we can draw a vertical line here, let us say for IA equal to 20 amperes. The total armature drop is 20 plus into 0.2 plus brush contract drop of 2 volts, this gives you 6 volts. So, the corresponding to 6 volts we draw two lines, a line parallel to the field resistance. This gives you two field currents E equal to approximately 0 and 10 2.5 volts. The corresponding field currents are IF equal to 1.4 ampere and 0 ampere. This is 2.5 volts. The corresponding terminal voltage Vt corresponding to this will be 102.5 minus 6 equal to 96.5 volts. Field current at that point is IF equal to 1.4 amperes. Therefore, the load current IL equal to 20 minus 1.4 equal to 18.6 ampere. So, one point on the corresponding to IA equal to 20 amperes is IL equal to 18.6 amperes, IF equal to 1.4 amperes and terminal voltage Vt equal to 96.5 volts. The other point is IF equal to 0 ampere, Vt equal to 0 volt, and of course Isc equal to 20 amperes. Since If equal to 0, IL equal to IA equal to 20 ampere, or If equal to 0. Now, when we include armature reaction, the procedure gets slightly modified, but it again starts with plotting the OCC and corresponding to 110 volt, the field current is 1.5 ampere, hence the load line this is 6 volts. Now, for again a Ia equal to 20 amperes, we know the AR AT equal to 1.5 into 20, that is 30, NF equal to 200, therefore, IF demagnetizing ampere turns in equivalent field amperes equal to minus 0.15 ampere. So, let us draw a line showing minus 0.15 amperes OC and a line OC equal to 0.15 amperes and a line BC which is equal to IARA plus EB is equal to 6 volts, and draw a line parallel to the field load line this intersects at Et equal to 95 volts, and the corresponding field current is 1.3 amperes. So, the intersection point is at intersection point IF equal to 1.3 amperes, E equal to 95 volts. So, Vt equal to E minus Eb minus IARA equal to 95 minus 6 minus equal to 89 volts, If equal to 1.3 amperes and IL equal to 20 minus 1.3 equal to 18.7 amperes. This is how one can calculate the terminal voltage of a DC shunt generator. Thank you.